All right, so 2.3 number 14 has this kind of generic, all right, so if you had some first order linear equation, right? So this is my kind of classic first order linear differential equation. What word did I miss in there?
Non-homogeneous?
Yeah, this one is specifically non-homogeneous. Okay, so they're saying, suppose you had something like this, right? And then they're saying, well, under one of our theorems, which is like 2.3.1 or something, right? We know some stuff. And then from another theorem that's, you're going to have to tell me which number this one is. 2.2.1? 2.1.2.
Yeah.
Okay, so there's these two theorems, and these both kind of apply and tell me something interesting. So let's see what they say. What do they say?
2.3.1 says if f is continuous on an open rectangle, a is less than x is less than b, c is less than y is less than d.
Okay. Okay, if f is continuous on this rectangle.
And it contains x naught, y naught, then the initial value problem y prime is equal to f of x and y.
With presumably y of x naught is y naught?
Yes. Has at least one solution on some open subinterval of AB that contains x naught.
Okay, so this is the existence and uniqueness theorem, essentially, right?
Yeah.
Okay, cool. All right, and then theorem 2.1.2 tells me how to solve stuff like this, right? So what does it say exactly? Presumably it says something like, if you have some assumptions and y prime plus p of xy is q of x. My assumptions. Okay, so my guess is that this is the theorem that says how to solve these things, right? So the how to solve it, yeah, it says this is a first order linear differential equation, right? So I'd like go find the homogeneous solution, right? And my solution for the homogeneous case is like e to the minus integral of p of x dx, right?
It says that you use the antiderivative of f over yh.
Yeah, and then there's some like, oh, well, you can use variation of parameters, and there's some form for the solution, right? Did you find the theorem?
Yes.
Okay, what's it exactly say?
P and f are continuous in AB, then every solution of that, which you already have.
So if p and q are continuous,
On AB, then every solution of that on AB can be obtained by choosing a value for the constant c in the general solution, and if x naught is any point in AB, in A and B, then y naught is arbitrary, the initial value problem.
okay, so I think it says essentially if p and q are continuous on some interval ab, and that your equation looks like this, then you solve doing some stuff, right? So like there's probably some more stuff here about how to exactly solve. And then it says, and the solution you get holds for all initial values in the interval AB, right? So what is the difference between that thing and this thing? So what is the difference between the specific, how do you solve this that gives you an, ooh. This one gives you a solution, right? This one tells you, like, dude, just do this stuff and you'll get a solution. That solution looks like this. You guys see that? And it works on all of A, B, where P and Q are continuous, right? So, like, as long as you've found an interval that's as big as possible for continuity, this is the solution and it works the whole time. Cool? As opposed to what the existence and uniqueness theorem says, which is substantially weaker. Because the existence and uniqueness theorem says what, basically? yo dude, there is a solution, good luck finding it, and also it's on sub-interval, possibly not the whole interval.
Is that,
You
does
guys
that
see
only
that?
apply to first order linear non, or?
This
Yeah.
existence and uniqueness there, this is basically the weak one that we have.
But it's for only,
Yeah, this one
Linear.
specifically takes equations
Okay.
of
you have it up there, I think.
this form,
Oh, okay, okay. Oh,
right? And this guy takes only equations of this form, right? And the reason I'm looking at this one and thinking, dude, that's a kind of a weak sauce existence and uniqueness theorem, is that this one, I mean, one, I don't even have the uniqueness part written up here, right? And two, it doesn't tell you how to get the solution at all. It just tells you there is a solution, and it doesn't tell you where it works. It just says it works for a little bit.
but that can apply to many more types of functions, right? So
Yeah, but this thing applies to more functions, whereas this guy, it might tell you how to solve stuff, but it's way more specific. Like, it's got to be written exactly like this, and everything like this fits into this guy, but not everything like this fits into that guy.
Is one linear, one non-linear?
Yeah, this one applies to linear,
Linear.
right? Because this is linear, non-homogeneous, first order differential equations. Like, that's what this guy does. This guy does possibly nonlinear. It does at least linear and also some more stuff. This one also does Bernoulli. It also does, yeah, there's a whole bunch more stuff. Cool? Does that kind of help? Like, the thing you get out of the specific solve it theorem is a lot better as long as you're in that specific solve it case. But if you're not in that case, then you maybe settle for an existence and uniqueness theorem, but that thing doesn't tell you much beyond, like, yo, it's not a waste of your time to go looking. You guys cool with that? Does that kind of make sense?